There's something lurking out there, stranger than black holes, deadlier than supernovas, and denser than anything you can imagine. A cosmic monster born of the death of stars, with the power to bend time, break atoms, and even send signals across galaxies. Today we dive into the mind-bending world of neutron stars, pulsars, magnetars, starquakes, and the terrifying possibility of strange matter that could consume entire planets. If you're looking for the universe's most extreme secrets, you've just opened the right door. In the vast tapestry of the cosmos, some mysteries hide in plain sight. Take the Crab Nebula, for instance, a growing cloud of gas and debris floating in the constellation Taurus. To the naked eye, it's just a beautiful smear in the night sky. But what lies at its heart is anything but peaceful. Almost 1,000 years ago, in the year 1054, ancient astronomers from China and the Middle East recorded a new guest star appearing in the heavens. It was so bright, it could be seen in daylight for weeks. What they witnessed was the violent death of a massive star, a supernova explosion tearing itself apart in a final cosmic scream. And what it left behind was something no one could have imagined. Because hidden inside that cloud is a star that's no longer alive, but still refuses to die. It spins, it pulses, it whispers across the galaxy in invisible beams of energy. A neutron star, so small, yet so impossibly dense that a single teaspoon of it would weigh more than Mount Everest. But how does something like that even exist? What does it mean for us? And could these stellar corpses hold the key to understanding some of the universe's most terrifying truths? Today we'll unravel the secrets behind these cosmic beasts, from the moment they're born in the fiery heart of a dying star, to their strange evolution in pulsars, X-ray monsters, and magnetars capable of twisting reality itself. We'll even explore the chilling possibility of quark stars and strange matter that might spread through the universe like a virus. This isn't just a journey into space, it's a journey into the unknown limits of physics, time, and maybe existence itself. All stars are born the same way, out of clouds of dust and gas collapsing under their own gravity. But how they die depends entirely on their size. And that's where things get interesting. Our sun, for example, will live a long, calm life of about 10 billion years. When it nears the end, it'll gently swell into a red giant, shed its outer layers, and leave behind a small, dense white dwarf. Peaceful, predictable. But not all stars are so polite. Some are 10, 20, even 30 times the mass of our sun. These giants burn hotter, faster, and die in a violent blaze. When they run out of fuel, gravity wins the final battle, and the core collapses inward in just a fraction of a second. Imagine this: a mass greater than the sun imploding, falling in on itself, crushing matter down with unimaginable force. The outer layers are blown away in a spectacular supernova, but the core, the heart of the star, keeps falling. And then something extraordinary happens. Atoms are ripped apart. Electrons and protons are forced to merge, creating neutrons. The entire core becomes a soup of subatomic particles jammed together so tightly that it resists any further collapse. This new object is tiny, about 20 kilometers across, but with a mass of up to 2 suns. That means it's more dense than anything else in the universe, except for black holes. To put it in perspective, if you took a spoonful of this material and brought it to Earth, it would weigh about 1 billion tons. This is a neutron star, a remnant of destruction, born from chaos, and yet it's just the beginning. because what happens inside a neutron star is even weirder than how it forms, and what it does to the space around it might just rewrite what we think we know about physics itself. Neutron stars are not just dense. They are nature's most extreme experiment, a challenge to our understanding of matter, gravity, and even time itself. Let's start with the surface. It may look solid, but it's anything but normal. We're talking about a crust made of superheated iron compressed to such an extent that it's harder than diamond and hotter than most stars, blazing at over 1,000,000 degrees Kelvin. But what lies beneath that crust is where things get truly alien. Under extreme pressure, the material morphs into bizarre shapes. Scientists call it nuclear pasta. Yes, pasta. Because the atoms stretch and twist into spaghetti-like strands, lasagna-like sheets, and gnocchi-like blobs. It's the strongest known material in the universe, 10 billion times stronger than steel. And deeper still, at the core, things may be even stranger. Here, matter may exist in a state we've never seen up close, a superfluid of neutrons, frictionless, silent, moving with no resistance. Some theories suggest it might even be a perfect conductor of electricity, and possibly hiding an even more exotic phase of matter we still don't understand. But the weirdness doesn't stop there. A neutron star's magnetic field is so powerful, it could wipe every credit card on Earth from hundreds of thousands of kilometers away. It's 1,000,000,000,000 times stronger than Earth's, and in some cases, like magnetars, even stronger than that. We'll get to those monsters soon. Even time bends near a neutron star. Einstein's theory of relativity tells us that gravity affects time, and neutron stars have such intense gravity that time itself slows down for anything near them. And if that wasn't enough, try escaping one. The escape velocity from a neutron star is over half the speed of light. Let that sink in. The laws of physics, as we know them, are on the edge of breaking down here. These objects bend reality in ways we're only beginning to grasp. But perhaps the strangest thing about neutron stars is that they're not quiet. They pulse, they spin, and some of them are sending signals across the galaxy, signals that first made scientists think we were not alone. What are these mysterious signals? Let's step into the strange world of pulsars. Not long after the first neutron stars were theorized, something bizarre began showing up in radio telescopes. Perfectly timed pulses, like a heartbeat, ticking from the depths of space. At first, scientists were confused. The signals were incredibly regular, so precise it felt artificial. Some even joked that it could be aliens. In fact, the first source was labeled LGM-1, Little Green Men. But the truth was even more fascinating. What they had discovered was the beam of a neutron star. You see, some neutron stars rotate, not slowly, but hundreds of times per second. And due to their powerful magnetic fields, they shoot intense beams of electromagnetic radiation from their poles, like cosmic lighthouses. But here's the catch. Those beams aren't always aligned with the rotation axis. So as the star spins, the beams sweep across space, and if one happens to point at Earth, we detect it as a pulse. That's a pulsar, short for pulsating radio source. And it's not just radio waves. Depending on their age and energy, some pulsars emit X-rays or even gamma rays, high-energy light that can only be detected with space telescopes. Jocelyn Bell, a young postgraduate student in 1967, was the first to catch one, a signal flashing every 1.3 seconds with eerie precision. That discovery changed astronomy forever. Pulsars are incredibly consistent. Their pulses arrive with such accuracy that scientists have compared them to atomic clocks. And by studying the small variations in their signals, we can detect things like planets orbiting them, or even ripples in space-time. That's right. Some of the first exoplanets ever discovered were found orbiting a pulsar, a dead star hosting alien worlds. Think about that. But as fascinating as they are, not all pulsars behave the same. Some spin faster, some emit different kinds of light, and some are part of a deadly dance with a companion star. And what happens in that dance is something you won't believe. Not all neutron stars wander the galaxy alone. Some are locked in a tight embrace with another star, caught in a cosmic relationship that's anything but romantic. These are binary systems, and in them, the neutron star becomes something far more terrifying: a stellar vampire. Here's how it works. As the companion star, usually a red giant or even a smaller white dwarf, ages and expands, it starts losing material. But it doesn't just float away into space. It gets pulled in. The neutron star's gravity is so intense, it begins to siphon off the outer layers of its partner. This stolen material forms a glowing disk that swirls around the neutron star like water spiraling down a drain. As the matter gets closer, it accelerates to incredible speeds and slams into the neutron star's surface, releasing bursts of X-rays so powerful that they can be detected from across the galaxy. These are called X-ray pulsars. And as the neutron star feeds, something else happens. It spins faster. Each drop of matter carries angular momentum, so as it falls in, it acts like a hand spinning a top. The more it feeds, the faster it rotates. Some neutron stars spin hundreds of times per second, transforming into what we call millisecond pulsars. That's faster than the blades of a kitchen blender, except that the blender is made of nuclear matter, weighs twice as much as the sun, and spins in a perfect rhythm. In fact, the fastest one ever recorded spins at over 716 times per second. Its surface moves at a quarter the speed of light. These aren't just neutron stars anymore. They're time machines. They're radiation cannons. They're the undead engines of collapsed giants, given a second life through gravitational theft. But even these incredible objects pale in comparison to what comes next. Because if you take a neutron star and give it the strongest magnetic field known in the universe, you get something else entirely. Imagine a star with a magnetic field so powerful it could erase every hard drive on Earth from halfway across the moon. A star so violent, its surface cracks from the inside out, releasing energy that can travel across space and still shake our planet's atmosphere. These are not ordinary neutron stars. These are magnetars, the most magnetic objects in the known universe. While most neutron stars already have incredibly strong magnetic fields, a rare few are born with magnetic fury on an entirely different level. We're talking about field strengths 1,000 trillion times stronger than Earth's. So strong that the very vacuum of space around them starts acting differently. And with that strength comes chaos. The crust of a magnetar is under constant, unimaginable tension. Beneath it, superfluid neutrons churn with electrical currents, while above, the magnetic field twists and strains against the surface. Eventually, something gives. The crust cracks, just a few centimeters in a sudden, violent quake. But this is no ordinary earthquake. This is a starquake. And the energy it releases? Enough to outshine an entire galaxy for a fraction of a second. In 2004, one of these starquakes occurred in a magnetar called SGR 1806-20. It released more energy in 0.1 seconds than our Sun produces in 150,000 years. Even though it was over 50,000 light years away, it still ionized Earth's atmosphere. We felt its echo from across the galaxy. If something like that happened within 10 light years of Earth, it would be the end. Our atmosphere would be stripped. Our oceans would boil. Life as we know it, gone. And yet, that power isn't even their final form. Because magnetars are unstable. Their magnetic fields decay over time, triggering more eruptions, more gamma-ray flares, more destruction. But they don't last forever. Magnetars are rare and short-lived. Still, during their brief existence, they produce some of the most extreme and mysterious phenomena we've ever observed, including strange signals that might not come from starquakes at all. Some scientists believe these signals, called fast radio bursts, could be coming from something even stranger. Something that happens when neutron stars collide. Two stars, both long dead, dense, silent, spinning in the dark, orbiting each other in a slow, fatal dance. This isn't science fiction. This is what happens when two neutron stars collide. Over millions of years, their orbit decays. They spiral inward, closer and closer, until gravity takes control. In their final moments, the two stars are moving at 2/3 the speed of light. Their magnetic fields intertwine. Their crusts begin to rupture. Space itself trembles. And then, impact. The collision unleashes a kilonova, a cataclysmic explosion that's as bright as 100 billion suns. For a brief moment, the universe blinks. But the real magic is in what's created. Because in that chaos, in those violent seconds of nuclear fury, the universe forges elements heavier than iron. Gold, platinum, uranium, rare earth elements, the building blocks of planets, and even life. Think about this. The gold in your wedding ring, the platinum in your electronics, the atoms in your bones, may have come from the collision of two dead stars billions of years ago. You're wearing the aftermath of a cosmic explosion. And these collisions didn't just make elements. They ripple the very fabric of reality. In 2015, scientists detected gravitational waves for the first time. Ripples in spacetime caused by colliding neutron stars and black holes. Einstein predicted them. And now, we can hear the universe breathing. But what happens after the collision? Sometimes the result is a black hole. Other times, the cores fuse, forming a heavier neutron star. Or maybe something stranger. Because if the pressure is high enough and the physics just right, something deep inside might break. Something that turns matter into pure quarks. At the heart of a neutron star, the pressure is unimaginable. Atoms crushed, electrons gone, protons and neutrons locked in place. But what if that's not the end? What if the pressure becomes too much, even for neutrons? In theory, under extreme conditions, even neutrons can break down, split into their most fundamental components, quarks. Quarks are the tiniest building blocks of matter. They're what make up protons and neutrons. And when they're freed from their confinement, something extraordinary may form. A quark star. Smaller than a neutron star, even denser. Composed entirely of quark-gluon plasma. A soup of subatomic chaos where the rules of normal matter no longer apply. But there's something even more unsettling. Some scientists believe that strange quarks, a heavier, more exotic variety, could create a state of matter so stable, so efficient, it might never decay. They call it strange matter, and if a chunk of it, a strangelet, were to touch normal matter, it could infect it like a virus, transforming ordinary atoms into strange matter, triggering a runaway reaction that could collapse entire planets into hyperdense spheres of exotic particles. Now, let's be clear, this is still theoretical. We've never observed a quark star directly, but the physics checks out, and some anomalous signals detected in space suggest we might already be seeing the fingerprints of something stranger than a neutron star. Something not quite dead, not quite stable, not quite anything we understand. But if this sounds unbelievable, wait until you hear what happens when a neutron star doesn't destroy its companion, but instead gets swallowed by it. We've seen neutron stars devour their companions. But what if the opposite happened? What if a neutron star was swallowed whole? Welcome to the strange and rare world of Thorne-Zitkov objects. Picture this: a massive red giant, bloated, unstable, nearing the end of its life. Orbiting close by is a neutron star, the collapsed core of a once mighty sun. As time passes, the giant's outer layers expand and the neutron star spirals in. But instead of being torn apart, the neutron star dives into the giant, beneath the surface, into the fiery depths. Now you have something straight out of science fiction. A star inside another star. On the outside, it looks like a normal red supergiant, but inside, it's a war zone. The neutron star orbits the core of the giant, disturbing everything: gravity, heat, magnetic fields. The structure of the star begins to change. Fusion is disrupted. Chaos reigns. Over time, the neutron star may spiral all the way to the core and merge with it. If that happens, the result is unpredictable. Some models suggest it could trigger a delayed supernova. Others say it might form a low-mass black hole surrounded by leftover stellar layers. Or maybe the neutron star survives for a while, hidden inside, burning with invisible fury. These hybrid stars are extremely rare. Only a few possible candidates have ever been found. But if confirmed, they would represent one of the most bizarre, unstable, and mysterious objects in the cosmos. A reminder that in the universe, the line between destruction and creation is razor thin. But what does all of this mean for us? Neutron stars, magnetars, kilonovas, and strange matter may sound like distant curiosities, but in reality, they've shaped the universe we live in, including you. We often look up at the stars and see beauty, but behind that beauty lies violence, chaos, power beyond comprehension. Neutron stars are the tombstones of dead suns, silent, spinning, and waiting. Yet without their explosions, their collisions, there would be no gold, no planets, no life. They are the universe's great alchemists. From death, they forge the building blocks of everything we know, including us. But this is only a glimpse of what the universe is hiding. Because just one video away, there's a story even more surprising, more mysterious, and it's something you'll never see coming. Click now and get ready to be amazed.